look at binomial distribution. And this is the theorem or the formula they've given you. So if you have two terms, we call the first one term A and the second one term B to some exponent, they've told you to go through this formula using, these are set up to be combinations as your coefficients in front of your variables. And then this one kind of tells you, and this is really the focus of it, depending on where your exponent is and what term number you are involved in here. So these are technically r's. So this would be the 0, then you have 1, 2, 3. This would be the r term. In order to figure out the exponent, you would take your exponent here and you subtract it by the term number in UR. So for instance, n minus 0 doesn't change anything. Here they had 1, that's why they had n minus 1. Here they had 2.
For this is b to the power of 1, but they just don't need to put it.
Here this is technically b to the power of 0, where that's how that same idea of n minus 0. And b to the power of 0 is just the value of 1, so they don't write it in the formula. Here, this is just b to the power of 1. That's why they didn't write it in, because this just assume if nothing's there, and that's where the r value is 1. So that's where they tell you the b term is r, and then it ends here at this concept here. Now this is a great formula to follow, but let's try to make sense of kind of where it came from. So Pascal's triangle is set up, and we'll start with Pascal's triangle, and then we'll relate it to all this stuff. Pascal's triangle is something you can build on your own to tell you how many coefficients you'll have in something, and it relates to the binomial theorem. So for instance, Pascal's triangle starts with the number 1, and then the triangle always has, it's built like a pyramid, and the ones constantly go out to the side, and you add the middle term. So this is kind of your start. You just have a 1, a 1, and a 1, okay? And that's the only part of the triangle you have to memorize. The rest of it you can do by application. The next term out, we just carry the 1, and we carry the 1, and the term in the middle, we add these two values together. So we get the number 2. 1 plus 1. Then we put 1 again on the outside, 1 again on the outside. We add these two together. 1 and 2 is 3. 2 and 1 is 3. Okay? The ones will always be on the outside. So we have 1 again, then we have 3 plus 1, which is 4. 3 plus 1, which is 4. And 3 plus 3 is 6. So it's a pyramid that continuously builds on and on and on. Okay? And these numbers help us figure out our coefficients in this binomial distribution theorem. Okay? So the idea is, think of it, and a binomial is when you have two terms. So we have, in this case, they have a plus b. Okay? The very first line is a plus b to the power of 0 here. And then the next thing we're going to do, the second line would be a plus b to the power of 1. So technically the second line is like this. Now if you remember this, to the power of 1 just means you have a and b. So if you look, the coefficient in front of a, for example, if I were to expand this, right? There's only one bracket, so I can drop the bracket. So this is essentially equal to a, b. And the coefficient here is just a 1 and just a 1. And that's what this triangle has told us, that it's 1 and 1. The next line would help you solve if you have a plus b squared. So depending on what math you did before, if you remember FOIL, you would technically have to FOIL this, yeah. And what you would end up with would be a squared plus 2ab plus b squared. That's what you'd get if you expanded this, okay? And what happens here is the triangle tells you the coefficients, okay, where we have a 1, right? We have a 2, and we have a 1 again. The next thing would be a plus b cubed. Cubed means we rewrite it this way 3 times, right? And that's a lot of work for us. So this triangle helps simplify that process for us. It'll tell us what our coefficients are. So instead of expanding this, I know by looking at my triangle, yeah, that means I'm going to have 1, and then a, and we'll put the exponents on after, plus 3, and we'll put an a and a b for now. Hopefully I can fit it in. Plus, I'm not going to really fit it there. 3ab, and then plus 1 again. And the only term is going to be, oops, I put that in red, is going to be b. So this is where we have to start figuring out our exponents. And this is where this idea comes in. Okay? Our exponents, if you notice the very first term, it tells you the exponent is to the power of n. Okay? In our case, the n is 3. So this would be 1a cubed. We put the 3 up there. This is how we help build it. The next one would be a, and you essentially just kind of count downwards with your a values. Once you have the top one, like these tell you exactly what they do, a or n minus the r value. So this is the first term in here, so we technically do 3 minus 1, so you get the number 2. But if you can just remember, just count downwards and upwards. So for on the left, we would go a is 3, then a is 2, then a is 1, and then technically a is 0 here. Okay, and you know what? I'm going to write it down here just so it's easier to see. We have 1a plus 3ab plus 3ab. I was getting too cramped in there. Plus 1. And actually, I'm going to write AB for all of them, just to show you this concept of how it's really being built. 1 AB. So you can always write it like this. And then 1 AB again. So say you're unsure how to build this and use these ideas. Well, this Pascal's triangle will tell you all the coefficients. Okay.
Is a question for this concept would be to, like, how do you build a Pascal's triangle?
They might ask you, and then they might ask you what coefficient would the third term be. This also helps you find like how many options there are with roots.
So it's a tool using stuff.
There's quite a few uses for it. And the one we're using right now is just a fast way to expand a binomial, and that's why they call it binomial distribution. It's because what we're doing is we have binomials, which means there's 2 terms in a bracket, and we're distributing them. We're just essentially expanding and simplifying. So that's what this tool, in this specific case, is used for. But there are actually quite a few cases for it. So again, the a value, we would just go like this. A3, 2, 1, and 0. And then you can do the exact opposite with your b's. If you want to count from the right down to the left, or if you want to count up from the left to the right, again, the b would be 3, 2, 1, and 0. So technically there is an AB attached to all of these, but b to the power of 0 is just 1, so we don't really write it in. And a to the power of 0 is just 1, so we don't really write it in.
So this is different than the binomial theorem?
This is actually the exact same thing. Yeah, it's just this is how it's built. This is another way of using Pascal's triangle to try and solve, where they ask you like how many terms are there in a binomial distribution to the power of 4, something like that. Okay, so you have to realize that a binomial distribution to the power of 0, there's only one term. This is actually equal to just the number 1. Anything to the power of 0 is just 1. So not only does it tell you what the coefficient is, it's 1, it tells you how many terms there are. There's only one number here, so there's only one term when we do this. Here, the 2 coefficients are the number 1, okay? And it also told us that there are 2 terms when we're the power of 1, okay? When we're to the power of 2, it tells us there are going to be 3 terms, and the coefficients will be 1, 2, 1. When it's to the power of 3, it tells us there'll be 4 terms, coefficients being 1, 3, 3, 1. And if it's to the power of 4, you're going to have 1, 2, 3, 4, 5 terms, these being all the coefficients. So it's a way to quickly distribute, because you might get a question, and you can use your formula as a fast way to solve that, but maybe we should try it right now. Say I give you something like this, a plus b to the power of 6. Okay? Instead of writing this formula out, where we have our FOIL and we write it many, many times over, we would use this. So take a minute. Why don't we try this right now? This way, and you still have to type in all of your calculator stuff, right? Yeah. Using my Pascal's triangle, I know this is technically power of 0. This is power of 1, power of 2. I write it like that because on a computer, that's how you'd write it. So power of 3, power of 4. Okay, I need to get power of 6, so I'm just going to extend this triangle. This would be 1, 5, 10, 10, 5, 1. I'm decent at adding, so I added them really quickly. Power of 5. And then power of 6 would be my next line. We'd go 1, 6, 15, 20, 15, 6, and 1. So let me just move this down a little. And lo and behold, I have already built all my coefficients, because this is technically to the power of 6, okay? So the next thing I have to do is just write AB plus, AB plus, AB plus, AB plus, AB. And I'm writing AB because those are my variables in there. Oops, AB plus, and then AB. So I've already filled in my coefficients quickly with Pascal's triangle, and then my exponents. Well, I know it's to the power of 6, so my a goes 6, 5, 4,
right, because you keep subtracting, right?
3, yeah, 2, 1. And then normally you don't write the 0 in, but it's not the end of the world. It's still technically right. And then for my b, I do the opposite. I just count the other way. 6, 5, 4, 3, 2, 1, 0. And boom. I've now distributed binomial to the 6th power extremely quickly, just using Pascal's triangle. I know it's a little cramped. I should have given myself some space there. But does that idea make sense on how to quickly do it instead of writing out all of the combinations?
Right, but when there's